Okay, bisectors of triangles. And we're going to talk about two different bisectors today, the angle bisector and the perpendicular bisector. And when you take a triangle and you find the perpendicular bisector of each side or the angle bisector of each angle, you get what is called what are called concurrent lines. Those concurrent lines, when they intersect, you get what's called a point of concurrency. Okay, so that's some vocab here, and we'll actually see that when we're going through these constructions. We're going to use the program GeoGebra to help us with our constructions. And you can actually do them using a compass as well, but we're going to go ahead and use GeoGebra. So I put the website there, and I'm going to go ahead and flip over to it there. So GeoGebra. Okay, when you get to this page, you want to click GeoGebra Geometry. And what we want to do is we actually want to find perpendicular bisectors of a triangle. But before we can do that, we actually need to have a triangle. So I'm going to go ahead, grab a polygon here, select polygon, and then I'm going to select 3 points. There, there, and down here. Okay, and then we'll bring it back to A there. So we've got ABC. And I want to go ahead and find the perpendicular bisector. So if you click on More over here, and then look down to where it says Construct, you have options, and we're going to construct the perpendicular bisector. If you hover over it, you can see what it says. And the way you do that is you select A, and you select B if you want the perpendicular bisector of that side. So there we've got it. If I want the perpendicular bisector of BC, I'm selecting B, and then selecting C. And then if I want the perpendicular bisector of AC, I select A and then C. And notice what I have right now is I have right angles. Okay, I have a right angle right here. Okay, I have a right angle right here, and I have a right angle right here. Now, when I'm grabbing the figure, I'm actually dragging it. So what I'm going to go ahead and do is label those points. So I'm going to call that point D, point E, and point F. We're going to call the point where those lines intersect, that point of concurrency, G. And so that's what I've got. I've got perpendicular bisectors. I've got the point of concurrency, which I have an acute triangle. And note that one of my questions here is the circumcenter of an acute triangle. By the way, the circumcenter is what that point of concurrency is called here. So this point of concurrency, point G, is the circumcenter. And so the circumcenter of an acute triangle is inside the triangle. Now note, if we actually change this triangle up here, and we'll make B an obtuse angle, B is now obtuse, and that point of concurrency moves outside the triangle. So that point of concurrency is outside the triangle with obtuse. Okay, so let's kind of fill this out here. The circumcenter, the point of concurrency, the circumcenter, that's the special name for it, of an acute triangle is inside the triangle. Circumcenter of obtuse is outside. So what does that mean about a right triangle? Well, now we can actually measure the angle here. So I'm going to go ahead and put an angle measuring tool. I haven't tried this for a while, so let's see if it works. So A to B to C. Okay, so there's our angle measure. Now I'm going to go ahead and drag that triangle again until I get to 90 degrees. And looks like I got it right, almost. Kind of tough. Oh, just had it. There we go. All right. Well, we're getting pretty darn close, and hopefully you're recognizing that if it's 90 degrees, that point is actually going to be on the triangle. For some reason, I can't get it to stop at 90, but just got two shaky hands. It's almost becoming a challenge for me now, so gotta not get so attached. But anyway, it'll be on the triangle right there. Okay, 89.6. We'll call it close enough to 90 there. Okay, so circumcenter of a right triangle is on the triangle. Okay, the circumcenter of a triangle is blank distances from the vertices. Okay, well, let's go ahead and measure that. We're going to go from, let's go ahead and make this triangle different here. Okay, we're going to go ahead and go from the vertices to the circumcenter. So I'm going to go ahead and take a segment and go from here to there. I'm going to go ahead and go from G to C. And I'm going to go ahead and go from G to A, out to the vertices. And I'm going to switch the colors on those. Okay, so, oops, I didn't mean to do that. So let me go ahead and select the trash. I trashed it there. I'm going to go ahead and select this line. Okay, and let's go ahead and change the color. Let's, I don't know, I'm colorblind, so this one looks blue to me, so I'm going to use that. Hopefully it's blue. Okay, select that line. Oops. Let me go ahead and try that again. Oh, it's supposed to let me select. There it went. There we go. And so we'll make them all the same color. For some reason, there we go. Okay, now we have them all the same color now. And notice if I drag this around, those segments are changing sizes. So what I want to do is I want to know what the measure of those are. So I'm going to go ahead and select centimeters here. I'm going to select the segment. Looks like that segment has a measure of 4. Select that one. Oop, that one's also 4. Select this one. That one is also 4. That's actually pretty darn amazing. I didn't get any decibels there. I'm going to go ahead and move those closer to the segment. You'll notice if I start moving that around again, those measures change. But they always stay the same. So the circumcenter is always equidistant to the vertice of the triangle. Okay? So if I'm writing that out here, let's go ahead. Equidistant. That's supposed to be an S. I'm writing on my screen in kind of a weird way because I'm using a stylus. I'm writing on it vertically, so my handwriting looks really worse than it usually is, but okay. So it's equidistant to the vertices. And what does that mean? Well, it means if I want to take a circle, so I'm going to go over here to my circle construction tool. Okay, circle through a point, and I want to select G as my center and pull that circle out until I get to like point C. Right there. So G to C. Okay? Notice that oops, let me get rid of this other circle. Okay. Notice that circle hits all 3 vertices because those segments, those blue segments, I think they're blue, the 4.2s, those are all radii of that circle. So if we start moving that around, I pull that, start moving around, notice all 3 vertices stay on that triangle, no matter if it's right, acute, or obtuse, they stay on the triangle there. Okay? So pretty interesting stuff there. That's called the circumcenter. You have a circle that goes around. Okay? The triangle is outlined by that circle. Hits all 3 points there. All right. So make sure we have that filled out there. Okay? So we also call this a circumscribed circle here. A circle that circumscribes, goes around and hits all the polygon and all vertices there. So a circumscribed circle is what that creates. Okay, we're going to go ahead and move on and kind of apply this in a different way. Okay, so let's switch it up here. Okay, and it says perpendicular bisectors of a triangle on the point of concurrency. So we're going to try a sample problem here. And this is also GeoGebra, so I'm going to select that website. And there we go. Okay, I also put it there so you could get to it. All right, so I've given you 3 points in this, and the directions: find the location of the point that is equidistant from points A, B, and C. So remember, if we're trying to find a point that's equidistant from 3 points, we could make a triangle out of it and then find the circumcenter. So, oops, let me undo that there. So we're going to select point A, go to point B, go from B to C, and then C to A. So that's another way of drawing a triangle rather than using your polygon tool there. Okay, and then from there, what we could do is we can construct the perpendicular bisector again. So A to B B to C, and C to A. And if we label that point, point G, okay, oops, let's try that again there. Actually call it point G. Well, missing my label. There we go. All right, we'll call it point D. Okay, that point, point D, will be equidistant from the edges there. So let's actually select this, and D to B. Oops, selected the wrong one. Go D to B, D to C, and D to A, and we can show that they're equidistant by putting our measurements on there. There, we got it. So point D is equidistant. All right. We also can do that by hand. So find the coordinates of the circumcenter of a triangle, and I've actually given you it on graph paper and plotted the points there. So we're not going to use a GeoGebra program on this. We're actually going to calculate the perpendicular bisectors on our own. So the first thing you have to do is be able to find the slope and midpoint of each side. Okay. So the slopes and the midpoint. So if we think of the slope here, first, currently the slope of AC is undefined. It's straight up and down. Okay, so that's undefined. The slope of BC, since it's horizontal line, is 0. And the slope of AB, if we just take the two in, we rise 1, 2, 3, 4, and we run 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's double check that. 1, 2, 3, 4, 5, 6, 7, 8. Oops. We run 8. So we rise 4. We run 8. So a slope of 4/8, also known as 1/2. Okay, so that means we could just go up 1 and over 2, and then go up 1 and over 2 again. 1 and over 2, and then 1 and over 2, and we're there. Okay, so that's our slope. Now to find lines that are perpendicular, we have to take slopes that are inverse reciprocals. Okay, well that's kind of easy if you're dealing with 0 and undefined. Slope that is undefined, the one that's perpendicular will be 0. And a slope that is 0, the one that's perpendicular will be undefined. If you want the slope of a line that is perpendicular to 1/2, you have to flip the fraction 1 over 2 and make it 2 over 1. And since it's positive, we're going to take the inverse, which is negative. So our new slopes will be those right there. And the midpoints of each side, well, if it's a horizontal line, it's pretty easy. The midpoint is right in the middle. Okay, so we go from 1 to 9, that's a distance of 8, so we go 4 over 1, 2, 3, 4. There's our midpoint. Okay. And the midpoint of a vertical line, same thing, it's just right in the middle. There it is. And the midpoint of this line, well, you can kind of see, rather than rising 4 and running 8, you could rise 2 and run 4, and that brings you right in the middle. You could also use the midpoint formula if you need to. Remember, the midpoint formula is equal to x1 or x2 plus x1 over 2 and y2 plus y1 over 2. Might be helpful if you don't have as nice of a figure there. And in this case, if we were using A and B, okay, you'd have x1 and y1 and x2 and y2. You just substitute those in and calculate it out. Okay, so you'd have 1 plus 9 here over 2, and then you'd have 2 plus 6 over 2. Well, that's 10 over 2, or 5. And 8 over 2 or 4. And that actually happens to be where we're at there. Okay. So once we have that, we are using our slopes. So the slope of going through this midpoint, slope of the line that's undefined, the perpendicular, is a flat line. Slope of a line that is flat or 0, perpendicular, is undefined. And you can kind of see where they're going to intersect already, but just to double check, you could put that last one in. This one would have to rise 2 and run 1 this way, and go down 2 and 1 this way. And notice there is your perpendicular line. Okay, you have your right angle here, it bisects, cuts in half, right? And you have your right angle there. This happens to be your point of concurrency, which is actually at the ordered pair 5, 4. So the circumcenter here is the ordered pair 5, 4. All right. Well, let's go ahead and try one last piece here. It's dealing with angle bisectors. So another point of concurrency is when you have angle bisectors, and we call that the in-center. So what I'm going to do is I'm going to have us go to a different GeoGebra piece here. Okay. And opens it up. It says find the location of the point that is equidistant from each side. So I've drawn a triangle here for us. All right, and what I want to do is I'm going to construct the angle bisectors. Now if I look at my constructions here on the page, over here I want to do I want to go to this angle bisector. And I need to select my angle. So if I want angle A, I need to go B to A to C. There's my angle bisector. Okay. And if I want angle B, I'm going to go A to B to C. If I want angle C, I'm going to go B to C to A. And that point right there in the middle, that is called our in-center, and we're going to go ahead and label that point D. Oops, that labeled my line there. That was not what I wanted. Okay, and now I need to go out from the side of from the in-center out to a side at a right angle. Okay, so we're going to go ahead and construct a line that's perpendicular from the in-center side. Okay, and then from the in-center out to the side. And from the in-center out to the side. Now all these lines start getting confusing, so I'm going to go ahead and label the points that I'm interested in here. So we're going to go ahead and call this point E. Again, we want it to show the labels. Point E, point F. That labeled the line. And point G. Okay. Now those distances right there, if we measure our distance out from D to E, from D to F, and from F or D to G, notice each of those has a measure of 1.52 currently. Okay. And then we could, if we start moving this this triangle around by grabbing one of the angles and just kind of looking at it, those measures all stay the same. So wherever it hits it at a right angle, they stay the same. Okay, and you can just double check if you wanted that it was a right angle by doing angle measurement, but I'm not going to do that right now. Okay, and the other thing that the in-center does, it allows you to take a circle and you could go through center D and out to one of those sides, say like F there, and it inscribes that circle inside the triangle, okay, and it hits all sides of the triangle at those points. All right. So what I'm going to go ahead and switch back to our PowerPoint here. It says the in-center of a triangle is blank from the sides of the triangle. Once again, that is equidistant. Okay, that is a special piece there. And if I wanted to go ahead, I'm going to go ahead and have that picture in there. Okay, picture of the one we just did. All right, and I've changed the color so we can kind of see those perpendicular lines. There's the perpendicular there, that perpendicular, and that perpendicular. So we're dealing with DG, DF, and DE, right? Okay. So using that information, let's go ahead and try a problem here. It says if DE is 3x plus 1 and DF is 6x minus 11, can we find DG? So if we know DE, this is 3x plus 1, and we know that DF, 6x minus 11, can we find DG? Well, they're supposed to be equidistant, so really if we can figure out what those two lengths are, we can figure out that. And the way we could do that is just set them equal to each other. We know that DE equals DF, and that equals DG. So 3x plus 1 for DE has to equal 6x minus 11, which is what DF is. Okay, and we do the math here. We subtract 3x over. We'll end up with 6x minus 3x, or 3x minus 11 equals 1. Add the 11 over, we get 12 equals 3x. Divide by 3, right? And we get 1x is 4. So x is 4. That means the measure of DF is 6 times x, or 6 times 4 minus 11. It's 24 minus 11, also known as 13. Okay, and you can just double check your work here and see if DE is the same. So 3 times 4, which is 12, plus 1, that's also 13. So DE equals 13. DF equals 13, which means DG must equal 13. All right. I think that's all I got for you. Good lucky.